purpose of this lab is to observe a falling object and to create a computer model that predicts the object motion in regards to the gravitational and/or drag forces acting on the object. The model used in this lab is a crumpled piece of paper that will be released from a certain height that we will designate to be zero with an initial velocity of zero as well. The fundamental principle used in this lab is Newton's second law of motion, which will be used by finding the net forces acting on the object to predict its velocity and positions over some delta t. Overall, the main result of the lab came from comparing the fall of the object predicted by computer models that either only included gravitational force or had both gravitational and drag forces. The overall result was that the model that included both gravity and drag force in calculating the fall of the object was more accurate than the other in predicting the ball's motion. Before observing the experiment and creating a coded model, it is necessary to look at the fundamental principle behind this experiment. This experiment relies on Newton's second law of motion, and the reasoning for this is because we are trying to predict the object's motion given the net forces, position, and vector of the object. The following two equations of Newton's second law will be used to predict the object's position and velocity over time. The final velocity of the object will be calculated through the net forces acting on the object, and which would be the gravitational and/or the drag forces. This new velocity will be then used to predict the new position of the object, and this will be repeated for an iterative calculation. The model of this experiment is a ball of paper that will be dropped from rest. From a certain height, this model is being dropped vertically without an initial throw. The reason for why this model was chosen was that because the paper had a light weight that would thus fall at a slower speed than the heavier objects, which will help the tracker program that we use to better track the position as the ball falls down. The system in this experiment is the ball that is falling down, and the surroundings are the net forces that are acting on the object, like the force of gravity and drag. Using a tracker program, the position of the ball will be tracked over a time interval of 0.33 seconds with a interval of 0.033 seconds, which is represented in this following chart. Utilizing this chart, we can identify the initial conditions to have an initial position at 0.005, which will be assumed to be 0, and at the 0 second time frame. Because the object is being dropped from rest, we are assuming the initial velocity to be 0 as well. Then this experiment was put into code to create models that best represent the position change of the ball. The mass of the ball was set to be 0.0031 grams, and the gravitational constant was incorporated to calculate the net force of the object. Small time intervals were set for the iterative calculations done in this while loop. Here we use the velocity update equation, as shown in the first few slides, and the position update equation over each time interval. However, because the net forces on this object is non-zero, the net force also had to be calculated in each step in which this current model only gravity was accounted for. Multiplying the ball's mass and gravitational constant give the weight or the net force pulling the object down. After iterative calculations, this chart shows the predicted positions of the ball. These values were compared to the experimental values in this chart, and this chart shows that the model was accurate in predicting the object's motion at earlier times, but started to over-predict the distance that it traveled at later time intervals. This is due to a drag force acting in opposition to the weight force pulling it down, which is represented in this modified section of code. Now the weight force is being opposed by a drag force represented by Fd in the opposite direction, indicated by this negative sign, and the magnitude is proportional to the square of the object's speed. The found proportionality constant was 0.0045, and the new net force included the addition of this drag force and the weight vector. The new predicted positions after including the effect of drag is now represented in this chart, where the yellow dotted line is the modified code, and the red line is the experimental code, and the blue line is only the gravitational force acting on the object. We can say that in this chart, the new model had a more accurate prediction than the model without the drag. To conclude, the aerodynamic drag force was critical in predicting the object's motion compared to using a net force without the force of drag. Some possible sources of error in this lab could have been the shortness of the frame width of the experiment, as the object could have had a better model of drag force at later time intervals. Another source of errors could have been the miscalculation of the drag force coefficient, as this was determined by trial and error for the coefficient value that predicted the object's final position most accurately. Between the models, the model that incorporates the drag force predicts the terminal velocity, or when the object reaches its maximum speed that it can have. The second model predicts this through the leveling off of the velocity, which shows that there will be a maximal or terminal velocity, unlike this linear model that only has gravity. Because terminal velocity occurs when the gravitational force is balanced out by the drag force, the acceleration or the net force on the system will be zero. What if the object was initially thrown downwards, then the terminal velocity would still be the same, as the object would eventually reach its maximal velocity, as shown in this velocity time chart for an object that is thrown down. Terminal velocity will only just be reached faster than an object at rest. Thank you for your time in watching this video.